This demo take advantage of improved 5G tools specifically suited for vehicle platoon communications, enhancing not only connectivity but fusing the decisions of autonomous vehicles with the radio resource allocation and physical layer adaptation. For supporting V2X communications, the demonstrator is composed by 4 major components: a digital twin platform, a V2X channel model, a 5G RAN simulator and management system, and finally a validation framework. Connected Car's digital twin platform in the demonstrator plays a key role to realize vehicular traffic generation, V2X messages, platoon maneuvers, and provides a graphical user interface where we can see related data. The Manhattan System Simulator here provides the 3D V2X channel model, which allows to perform the signal propagation and implements interference detection and 5G massive MIMO to improve the reliability of the network. On top layer was implemented framework called ONAP, allowing to manage and perform the lifecycle of the network. Following the O-RAN architecture was implemented a control loop for network optimization based on RAN metrics collection. Also, a RAN simulator was developed to perform physical layer and MAC features with support for network slicing on cell capacity. 3 use cases were studied, and we started with the first case, which is latency emergency braking. Starting by the V2X channel model, that was integrated in different partners' components, as we can see on the right. Architecture implements a geometric distribution of scatters, contributes with different delays and phases that are randomly distributed. The Manhattan grid was used, where the geometric configuration of walls, ground, base station was used for the calculation of all deterministic rays. In this scenario it was assumed that the base station can relay the signal to the rest of the vehicles to trigger the emergency braking. In this scenario, a platoon is crossing the Manhattan area, connected to the base station and attached to a default network slice. Using the Manhattan channel model we can get the SNR values, allowing us to later to obtain latencies and throughput and packet loss ratio. During the simulation, vehicle data is being propagated by CCDTP, allowing us to have the itinerary of the platoon, and its speed. With this we can model our simulation, allowing us to have an approximation of a real vehicle behavior. During the simulation, the messages are generated with high frequency. Here we can see a sample of messages captured by Wireshark. In case of emergency braking, we can use a base station signal to detect the presence or absence of a line of sight. In this case, convolutional neural network algorithms were used based on characteristics of radio propagation. In this scenario, it was assumed that the base station can relay the signal to the rest of the vehicles to trigger the emergency braking. The use of SIG-NOMA with AI has shown improvement of capacity, allowing to reduce latency and allows adaptive retransmission. This combines different signal processing tools, dealing with interference and with jamming, fading and security. During the RAN simulation was detected a high packet loss rate due using general network slice. Latencies also increases since we have a high packet rate. At this point, and as part of the control loop, the RAN metrics such as throughput and packet loss are sent to VES collector on ONAP platform, allowing the prediction of cost degradation. From the connected car's digital twin we can see that high packet drop can originate a collision in the platoon. Then the RAP uses the metrics collected based on threshold cross analytics and verifies if we met required SLAs, which is not the case. To mitigate this, a policy is created and sent via A1 terminator the RAN to optimize the network. Slice allocated PRBs can change according to inter-slice scheduler decision with a custom granularity. In this case, enforcement was carried out to create an ultra-low latency slice. With low latency network slice on RAN side, we observed that the packet loss decreased. Next use case covers the V2X interference traffic congestion. In this second scenario, we have increased the number of cells and vehicles that will cause interference and traffic congestion. Following the same line, we started with a common network slice for all users. High packet drop rate can reduce user safety by missing CAM or DENM messages. It's possible to verify that with this configuration we got high packet drop. Then, using the control loop, the metrics are collected. In the same line, and as we can see on the logs, a policy will be created, where this will enforce the creation of a new network slice for vehicular platooning with low latencies. From the dashboard we can see two slices now created in the cell number 1, enhanced mobile broadband and ultra-reliable and low-latency communications. Numerology, subcarrier spacing and allocated physical resource blocks are set for each network slice, allowing to serve different services. From Connected Car's digital twin dashboard, we can see on the map that the red indicator shows the message received by the vehicle when the packet drop rate is low. In this case, the network slice with low latency improved the latency and reduced the pack drop. Connected Car's digital twin platform can receive various commands from a platoon coordination system to change their behavior. Initially, both platoons in the scenario are moving at 10 meters per second. The speed command is sent to the platoon 1 and increases the speed of the vehicles within the first platoon up to 30 meters per second. The inter-vehicle distance of the vehicles within the scenario can also be changed. The commands from the platoon control center can be used to monitor the traffic and adjust the platoons with the aim of enhancing safety and traffic flow. The last use case is the platoon wireless resource management in tunnels that we will see next. V2X communication of platoons in tunnels is demonstrated in the Connected Car's digital twin platform, which includes simulation of the physical conditions of the environment, generation of real V2X messages, and the physical layer simulation of the network. On the top, the platoon is subject to high packet drop, whereas on the bottom the packet drop is low. It can be seen that when the packet drop rates are high, the platoons are not able to react in time to prevent collisions. The Manhattan Channel model was used to test several scenarios inside the tunnel. We have tested the use of a base station with limited MIMO inside a tunnel to improve efficiency. Here we can see an element of channel distribution in Manhattan grid versus tunnel propagation, and we observe a fading distribution created by the different walls and ceiling of the tunnel. Increasing the number of antennas at base station side contributed more to reduce the latency, by counteract the fading distributions, of the platoon communications, rather than the increase of number of antennas at the vehicle side. With this we conclude the demonstrations based on system simulation for 5G vehicular platooning. Thank you.